Okay, let's move on to quantifying wave loss mathematically as a function of material properties. And so let me just start by kind of writing down some of the notation that we saw in the last lecture for perfect ideal attenuation. We had this notion of beta, the wave number, which equaled omega times the square root of mu times epsilon, the permittivity times the permeability. Both mu and epsilon were assumed to be real numbers in that case, in which case this would also be written as omega divided by the propagation velocity. And this is what we call the wave number. Right, so this is the lossless case or the ideal scenario. For lossy propagation, we're going to replace beta with something called gamma. Right, so gamma is going to be written as alpha plus j beta. Beta will effectively be the same thing as before. It's going to tell us how the phase is changing as a function of distance. And alpha is going to tell us something about how the amplitude of the signal is attenuating with distance, how it's weakening as a result of the material. Right? Beta can be written as, no, I should not go up here. Beta can be written as the imaginary component of gamma, and alpha can be written as the real component of gamma. And so to describe propagation of radio waves for lossless case, we basically had e to the minus j beta z. Describes how the amplitude and phase of an electric field changes. So the electric field as a phasor will equal to the phasor at z equals 0 times this factor e to the minus j beta z. Let me write this a little bit cleaner. All right, this is the electric field as a phasor. Take the electric field at the origin and multiply it by e to the minus j beta z. For lossy, it's going to be something similar, except instead of a j beta, we're going to write it as a gamma. So the electric field as a phasor going to be the same. Take the electric field phasor at the origin and multiply it by e to the minus gamma z, where gamma equals alpha plus j beta. So it's got the real and imaginary components within it. Right? So the only thing we need to now know is what exactly is this gamma and how do we solve that? So if we know gamma, we basically have our answer. Because again, the real part is going to tell us the exponential decay rate of the electric field, and beta is going to tell us how the phase is changing. And so I'm going to give you a formula for gamma directly. Gamma equals j times omega times the square root times mu times epsilon effective. Right? There's basically an effective permittivity that's going to take into account both the lossy dielectric as well as the conductivity. And epsilon effective is going to have three pieces to it. The first is the real permittivity that we've been dealing with so far. That's the response of the material to applied electric field, the realignment of the molecules. So this is just pure regular dielectric. Right? The second component is going to be the lossy part of the dielectric, or the sluggishness of the molecules realigning. So this is going to be a j times epsilon double prime. This will be the lossy dielectric. And finally, we're going to include the conductivity, and that's going to have a negative j times sigma, the conductivity, divided by omega. So this is going to count for the losses from conductivity. So I'm going to call this conductive losses. Right, so if you know the lossy dielectric and you know the conductivity, you can calculate an effective value for epsilon. It's going to be a complex number, but take that number and plug it into this formula. And that's going to give you a value for gamma. And gamma itself will have a real and imaginary parts. And as we showed up here, the imaginary part of gamma will tell you how the wave is propagating, and the real part of gamma will tell you the attenuation rates. So beta is radians per meter, and alpha is that weird unit meters per meter, which is how many 1/e reductions are you seeing for 1 meter of propagation. All right. Sometimes instead of gamma, you'll see a k factor. Either one works, but k is sometimes written as basically the same thing as gamma except without the j. So it's k times square root of mu times epsilon effective, in which case the electric field would vary as E0 times e to the minus j k z. So k becomes a straight equivalent of beta, except it's a complex number. So gamma and k are basically the same, there's just a difference of j between them. All right. Now in the notes, I have a direct side-by-side comparison showing exactly how the lossless and lossy cases correspond to each other. It's basically this comparison that I have here, but much more. But let me just emphasize that once we have this formulation that the electric field phasor as a function of z is the electric field phasor at the origin times e to the minus gamma z, we can decompose gamma into the real and imaginary parts like this. So it's e to the minus alpha z times e to the minus j beta z. And this alpha z right here corresponds to the attenuation. And the beta z is propagation. So if we were to plot this and convert it back into the time domain, we're basically going to see the following. We'll have an exponentially declining envelope. And this envelope basically follows the form e to the minus alpha z. And underneath that, we basically have a propagating sine wave like this. And so this is the actual wave in blue. And this wave is moving to the right in time. Right? So let me just give you one more form for gamma. In addition to this j omega times square root of mu times epsilon effective. It also can be written, if you plug in the formal formula for epsilon effective, it's also equal to j omega times the square root. As square root goes over the whole thing. This becomes square root of j omega times sigma plus j omega epsilon. Right? This is an equivalent way to write gamma. Depending on which form you like, they will give you the same answer. Right? So that concludes basically the math of how we take material properties, in particular the dielectric constants, both real and imaginary part, and the conductivity, and we can immediately calculate how the wave propagates and how quickly it attenuates. In part 3, we're going to consider a special case of a good conductor, which means that it has a lot of conductivity or a lot of dielectric loss. And we're going to see how that impacts radio waves. Now, the name is ironic, as I'll talk about later, but it's useful for a few different contexts, and we'll get into that in the third and final lecture video.